네,
So, hello, my name is Jae Won Kim, and I participate in the SURI program at Arizona State University, where I worked on research projects involving carbon nanotube fiber and copper-coated CNT composite fibers. These projects focus on how the internal structure of these fibers affect their electrical and mechanical performance. Carbon nanotube are nanomaterial with excellent properties. They are lightweight, strong, and conduct both electricity and heat very well. When assembled into the fiber form, they can be used in flexible electronics, energy device, and aerospace wiring. Coating CNT fibers with copper improves their electrical conductivity. Copper creates conductive pathway that connect the interior and exterior of the CNT fiber, making it easier for current to flow. As a result, copper-coated CNT fiber are considered promising material for next generation cable. They are lightweight, electrically conductive, and mechanically strong. However, performance is influenced not only by the material itself, but also by the internal structure of the fiber. For example, how well the CNTs are aligned, how densely they are packed, how boils are distributed, and how uniformly the copper is coated are all important. Therefore, understanding how these structural elements affect performance is essential, and this is the central focus of my research. In this study, two representative spinning methods were used to fabricate CNT fiber: direct spinning and wet spinning. Direct spinning is a process where CNTs are continuously thrown into the fiber form during catalyst assisted CVD. Wet spinning involves dispersing CNTs in solution, followed by alignment and drawing in a coagulation bath. Direct spun CNT fibers tend to have a loose and porous structure, allowing deeper coated infiltration. In contrast, wet spun CNT fibers are highly aligned and dense, causing copper to be mainly deposited on the surface. Based on cross-section analysis, we observed six types of copper morphologies. Type 1, Type 2, and Type 3 were found in direct spun CNT fiber, while Type 4, Type 5, Type 6 were observed in wet spun CNT fiber. Type 1 has scattered copper particles on the fiber surface. Type 2 shows partial copper penetrate between CNT bundles. And Type 3 contains copper that is uniformly distributed inside the fiber. And Type 4 has a noticeable gap between the CNT core and copper shell. And Type 5 has a reduced interfacial gap, the partial infiltration. And Type 6 forms uniformly core shell structure around the CNT fiber. To analyze this structure, we use cross-section images of CNT and copper CNT fibers, which were binary and processed using MATLAB. From these images, we extracted three key structural parameters. The first is the shape factor, which indicates how circular the fiber cross-section is. The second is packing density, which reflects how densely CNT fills in cross-section. The third is copper volume fraction, which measures the proportion of the area occupied by copper in composite fiber. Now, I will explain how these structural parameters relate to fiber performance. In the control plot for pristine CNT fibers, high shape factor and high packing density are associated with increased electrical conductivity and tensile strength. In particular, when the shape factor exceeds 0.7 and packing density was above 95%, conductivity reached 12 million Siemens per meter, and tensile strength exceeds 4 gigapascal. in the copper-coated CNT fiber, copper volume fraction was the dominant factor. Even when the shell factor decreased, if the copper volume fraction was around 50 to 60%, conductivity reached 50 million joules per meter and tensile strength around 0.8 gigapascal. This is because the copper fills void and forms continuous pathway for current and strength transfer. However, when the copper content became too high, the fiber became heavier and less flexible, reducing mechanical performance. In conclusion, this study demonstrates that the internal structure of CNT and copper CNT composite fibers has an impact on their electrical and mechanical performance. By analyzing cross-section image using MATLAB, we quantify shell factor, packing density, and copper volume fraction, and visualize their correlation with performance. In future work, we plan to conduct FEM simulation based on real cross-section image to better understand how void distribution and copper CNT interface influence charge transfer and load transfer. Thank you for listening.